surfaces with vector equations, also called parametric equations or parametric curves, what you're doing, so here we're using the variables u and v as my parameters. Okay, so they're just arbitrary letters. But notice what, so like this noodle shape, what this is right here is explaining the formula that would trace x. And this right here is the formula that explains how to trace y. And this is the formula that explains how to trace z. So you could see these sines and cosines within there. If you do square these and add them, you'll notice you'll have a cosine squared and a sine squared, which would create a circle. Remember, a basic equation of a circle, if you have cosine squared theta plus sine squared theta equals 1, it's another way to express the unit circle. So when you see sines and cosines, like if you're just looking at this, expect to see some circular pattern within. So we actually have two different circular patterns going on, because you have cosine of v here, and notice we have sine v in both of these other ones. So again, if you squared these and added them to this one squared, you create a circular pattern. So you see how it's curling, so you're getting a circular pattern in the xz direction and in the yz direction. You're also getting circles in this direction too. So again, we're not going to get as involved as the noodle things that I was showing you, but I'm trying to point out how you could somewhat match up if you were given a list of these kinds of parametric equations and a bunch of shapes, how you could kind of match them up if there's some clues to what would be going on. So you have sine of v and cosine of v, you have cosine of u and sine of u within these. That's an indication that you have different circles going on, hence creating that shape. Okay? The main thing to understand at the moment is that you can trace surfaces with vector equations, and what you're doing is you're figuring out or given a formula that explains how to trace x, a separate formula that explains how to trace y, and a third formula that explains how to trace z. And so then if you're plugging various values in for u and v, or whatever your parameters are, then you're calculating individual points on the surface, and if you calculate enough of those points, you can get a visual of what the surface looks like. And this is actually how computer programs will tend to graph things, even spheres. They will tend to graph things in this method, like they're programmed in the background to graph things with vector equations, and that's why you often see them drawn with these contours. Like we've got contours going in this direction, kind of helping us see the roundness of it in the tubular direction, and then we've got other contours like this, kind of helping us see the other bigger spiral. So if you see a computer graphic with those kind of contours, it means that in the background it was actually drawing it with parametrics. Yeah, Robert?
Yeah, even 2D images, there are a lot of applications where they'll use vector equations, based drawings. There's a lot of reasons why those are used. For example, they're infinitely scalable, other types of images aren't.
Kind of like what we were seeing in linear algebra yesterday.
So I mean, it's like the difference between having a formula and then having points on a graph. you know, a lot more with the formula than you can with a few points off of the graph. It's used a lot of places.
Yeah, no, that's helpful, Robert, that's interesting. I can see, and I think that article that I printed for the linear algebra class, that was kind of getting it without talking specifically about, I think if you analyze more deeply